Okay, what we got here is the intersection of Boulevardy and 281. I'm doing a little flying here, so I got all my flight stuff in the car. And what we're going to do, we'll see what this guy's going to be up to. There he goes. He made it. Okay. I'm going to be doing a little shifting here. As you can see, I got the wings of my gliders and my video film and all that. I was doing a little videoing this morning. What we're going to talk about as we drive down the road, 3.9 miles, which should be just about the length of a normal video. We're going to be talking about spin and about how precession plays such an important part of spin. Now, if you've looked into PDLs, partial differential equations, which of course come from Hamiltonian reworking of Newton's differential equations. These are new ways to look at differential equations that basically Newtonian math gives us, and the German guy, I'm sorry I forget his name, but they came up with a way of doing relating things, and especially relating things to gravity here on Earth. And of course, if you stick with that classical approach, what you're going to get is a very difficult time figuring out what motion's all about. And we have a lot of, now, there's a lot of equations that are supposed to formulate motion and what motion may or may not be. But before we jump into the math, you have to consider what math is. Math is a language. And that language is one, as all languages, uses metaphors. And that is, we relate things in our environment with words, and those words later, because they're verbs and actions, we attach other meanings to and other objects to. And pretty soon we can develop images, because that's the way our mind works. And we can talk about the environment we live in. And math does that. It is a language that uses symbols and tries to get us away from our normal language, because we think that those metaphors may not be apt. So therefore you have to have a faith in the language of math, that it is a truer representation than our of the universe and the laws of it and motion and the things that take place here than our own language would be, that our own observation would be. And the problem with that is that what we're trying to do in math is we're trying to represent action. We're trying to represent force and power, and we're trying to measure events. And these events are, of course, tied to motion and gravity and the fundamentals. And in those measurements, we hope to get a truer picture of how mass itself would work by measuring it. It's like, like at the state fair, you go out and you measure the bull there, and that should tell you what kind of bull he is. Well, we know it goes a little deeper than that, although it's not a bad way to measure things. The state fair and apple pies and pickles and bulls and brass balls and things like that. Gives us a lot of insight. However, that is failing us. And the reason I say that is we haven't got there, and we've had since Newton's time over 100 years to work this out. And I believe our mind works a lot faster than that. So I believe that there is a problem with the language of math. Hamilton looked at it, and he saw some of these problems. And I think, in the end, the fundamental statement is that it hasn't given us what we thought it was going to give. So maybe we should turn back to the Aristotelian and Socrates approach, and that is use our language. I chose English. And I believe, of course, I'm a native speaking English person, Celtic by, traditional lines of culture. So what we have to say is that let's try this language thing. And for you math people, I'm not saying that math is wrong. I'm saying that you're going to really help once we get the fundamentals, the 3 to 4 laws that should help us understand motion. And that's where we're going with this. I'll redo this one again and see if I can make my points better, because I know I've missed a couple I wanted to make. But this was right after a flight and some video things I was doing. Okay, so we'll close off here.